Well, hi again, everybody. Well, today I'm going to go back to my roots a little bit. This video is going to cover a piece of electronic equipment and a technology that I originally was planning on having much earlier in my career on YouTube. But it got pushed off because I didn't think many people would be interested in it. Although now I've heard a lot of questions being asked about a computer language called Verilog. So that's what I'm going to cover in this video, but I'm going to do just sort of an introductory discussion. We'll see how it goes. If people show interest in this topic, then I'll be glad to give more detailed videos in the future and go over it in things on how to use it in much more an elaborate detail that I'm going over here. So the first thing I'd like to talk about is what is Verilog in general? Well, Verilog is really not what it sounds like it is. People refer to it as a computer language, but it's really called a hardware descriptor language. And the main difference is Verilog does not produce executable code. You can't load it into your computer from a USB or from a hard disk and run it. It's not that type of language. Verilog, or more accurately called System Verilog, because they merged a few years back two different versions of it and they took the name of the more powerful one, is one of the two leading hardware descriptor languages, as I mentioned earlier, or HDLs, that are being used today in designing digital logic for computer systems. They actually use this language to actually go through and create the actual logic that will be composed within the large-scale integrated circuits that make up electronic equipment, computers, everything that needs integrated circuits as their base technology. And this is used throughout the world. It's been used for a number of years now. If you go back to its origins, it's probably about 20 years at this point. But more recently, the last 10, 12 years have been really the growth in this area. Prior to that, engineers sat there and designed hardware simply with the logic gates and Boolean algebra. And I can tell you, since I was included on my PE exam, doing it that way is the real hard way to do it. It takes a lot longer and much more prone to error. The other HDL, just to mention it by the way, is called VHDL, and that stands for VHSIC-HDL, or Very High Speed Integrated Circuit HDL. And it's meant for like super high speed equipment, and it's optimized for the speed on that type of equipment, or that type of equipment will actually need. So the syntax is different, although the basic, the basic principles that the languages use, both of them, Verilog and VHDL, are the same. The syntax, in some cases, is much different. I won't be covering VHDL in this video, but I could in a follow-up video if there's any interest. Now, what I'm showing here is a piece of Verilog code in the top part here where it says Verilog code, obviously. This is an actual Verilog module. It's missing a lot of the basics that it needs to compile properly, and they still call it compile, although some of the tools refer to it as being synthesized, which is probably a little more accurate. Although it's done in phases, it gets compiled and then synthesized, but ultimately it creates logic. It creates digital logic, and that's what's shown for this example. The actual one single line statement that I have there is an assign y equals a and b and c, or, because of precedence, those three ands go together, not a and not b, or a and not b and c. Now, this is not a simplified Boolean algebra equation. If we go through Boolean mathematics with that, we could actually break that down to a much smaller equation. But I didn't bother doing because I wanted to show the basic thoughts put on paper. So you have an idea that you want a piece of logic that does these three things. What do you need to produce to get that to work? Well, one sample is what's shown in the synthesized diagram that's right below it, and that's in digital gates and circuits that relate to that particular description. But it's not optimized, as I said. This would be a much less, right now it's using what, 6 gates In order to do that, 3 AND gates, an OR gate, and 2 inverters. It probably will get away with maybe 4 of those when it was simplified. We'll talk about that more. Just to show you how the syntax is, how it's similar in a way to regular computer programming languages, sort of like a combination of C or C++ really, because it is closer to that type of abstraction. But this shows you how you would do comments in the top. So a comment, you can do a single line comment or a multi-line comment. So there's an example right below that. There's a statement. Actually, it's actually a declaration of variables, logic, L, M, and N. That's a type of variable in Verilog, logic. And there's a comment there that says, these 3 are meant for internal loop state holders. So if you're going to create for loops, or case loops, or anything that reflects to choice within a piece of Verilog code, then you would use these as the variable that it uses as internal counters. So that's what that means. Now right below that are assignment statements. These are real statements that also show the difference between Verilog and other regular programming languages. The first one looks pretty straightforward, and it's something you would see in almost any other language, where you would say A equals B, and where I put operator, it would be something like plus, minus, and, or any sort of other operator that's applicable to the language. One thing to note as long as I'm here is that Verilog is a logic-based language, so you're going to see a lot more of the ands and ors in it than you would of pluses, minus, multiplies, and divides, although those are all usable within the language for various purposes. But the one below that, it's a different type of equal. It's actually considered a parallel instruction equal sign. If you want 2 statements in a regular programming language to execute, you put them in order. So the first statement might be something like A equals B plus C. The second statement might be D equals A times 2, or E equals 4 times 1, or whatever you want it to be. In Verilog, though, since it's creating logic, and it's creating logic on a chip that can run with parallel functions at the same time, then you need a special operator for that, and that's what they have in the bottom statement there. The A less than equal, that's not what it means. A less than or equal. There is a less than or equal operator, but in that position, right after the initial variable, that means to assign, and to do the assignment in parallel with other ones just like that. So if we had an A assign B plus C, the next statement had D less than equal, which is assign, F or Z. Well, those 2 statements, even though they appear in the code sequentially, they would execute in parallel. And that's a very important point to understand when you're creating logic, that you can create little bits of logic that will actually function at the exact same time. Now here's an example of some of the most popular, not all, but some of the most popular Verilog operators. And they're in order of precedence. Which ones will have precedence over the other? Just like I showed you in an earlier slide, we had the case where we saw an AND operator, the ampersand, which is toward the bottom there, 4th from the bottom. And then we had the OR operator, which is 2nd from the bottom. That means that they appear in the same statement, like I did in that first statement that I showed you, then the ANDs would be done first, or in this case, the equivalent of a logic AND gate would be done first. And then the OR NOR gate, that would be done second in terms of mathematical precedence, just like in basic math. I won't go through all of these operators, but again, I'd be glad to make a follow-up video going over how all of these work if you're interested. Now let's go through what we call the Verilog engineering process. This shows what's going to take place here in terms of developing logic with Verilog. But let me show you a very high level, because there's a lot more steps that I'm going to show here of how this engineering process works. The first thing you start with is creating your Verilog source, which is just a regular source file which you can create with a standard text editor or any editing software. I'll show you later on a package that's available for producing logic with Verilog or VHDL or other languages as well. But it's really just a basic editor. Some of them are easier to use and more fancy than others, but they're still editors. After you have the source code, what you need to do is you need to synthesize it. Now there's two steps to that. It first compiles, then synthesizes, but I'm not going to break that down here. And it uses CAD software. And the CAD software, that's computer-aided design software, specifically for this purpose. And I'm going to show you one in a little bit that is used, one of the more popular ones, that's freely available to learn with and to do basic projects with. Once you've synthesized it, then you software simulate it. That synthesized code in an intermediate form can be put through a modeling software that can actually simulate it running and actually produce for you right there on the screen how the timing would be at the output of every single chip that got, every single logic gate that got produced by the Verilog code. And that is also CAT software, computer-aided testing software. Sometimes they're integrated together and sometimes they're not. In the case of the same software I mentioned before, they have a separate module for doing advanced modeling. And the advanced modeling allows you to actually check timing. That's very important with computer logic. Then you go through what's called a hardware simulation. Now, this is the niftiest part in my mind. As a matter of fact, I'll show you some more later, but I have this board that I haven't used since I was preparing for my PE exam. And this board here is an actual hardware simulator for producing digital logic. It gets its input from the code that synthesizes the Verilog code into logic. That logic can then get loaded onto this. In addition to a dual-core microprocessor, it has a part of it that's called an FPGA, and I'll discuss that more later on. But it actually can take synthesized logic into it and replicate that logic within the chip. And then you can have it actually run, I mean really run the logic. This particular board is meant for that purpose. It has built onto it, if you look carefully at it, it has built onto it all sorts of options. It has toggle switches, it has push buttons, it has a lot of LEDs that you can't see easily on the camera here, but I'll put up diagrams later to show you more about it. And it has all the features of a personal computer as well. It has audio lines, it has, in this case, only a VGA connector, but it's usable. You could convert that out to an HDMI if you wanted to. I do have a converter around here somewhere. It has a Cat5 10BASE-T 1 gigabit Ethernet adapter. And this little chip here, the microprocessor part, can actually run a version of Linux. And you can use that to actually do testing of the FPGA. So part of the testing, once you've got it synthesized onto that card, can be done by another system running on the same chip. It is absolutely amazing. So that's the hardware simulation part. And it is based upon an FPGA, which stands for Field Programmable Gate Array. I'll talk about that more. And then finally, there is what we call an object output. There's a different name for it, but it's the same as dealing with an object output from a compiler on a computer program. It basically is just a series of configuration instructions that can come out of the software, and they actually fabricate the chips onto silicon with those object modules. They're not easy to decipher, so the actual object code itself is not something that would really give away the design of the actual chip internal, but the Verilog source code would, especially if you have comments, as all developers should, or in this case software engineers and hardware engineers should have on virtually every line of their Verilog code. And that is done, the fabrication, by a robotic automated plant of some sort. Usually it's a clean plant, dust-free. Human beings probably don't touch most of it. They probably load in initial raw materials. They load in the object module into their computer that controls the chip fabrication equipment, and that's really all they have to do. When they get it afterwards, then they have special testing equipment to make sure, and cutting the equipment that cuts the chips into smaller pieces. Although I understand a lot of them, they send that to another factory to do that process, because it involves different equipment that a particular factory that goes through a lot of this may not normally have. But I'm not going to get into that too much. But here's the Field Programmable Gate Array, FPGA. Now, the FPGA is, let's just imagine a giant array of hardware logic, but it's special hardware logic. Hardware logic that can read a configuration file and then be any kind of piece of hardware logic you want it to be. It can be an AND gate, an OR gate, a NAND gate, an inverter. It can be a flip-flop. Not going to get into what all those things mean right now, but I could in a follow-up video. But it can be turned, each one of these little logic components on that FPGA can be turned into whatever you need it to be, and it has the ability to wire them up to each other in any way that the original synthesist had told them to wire it up. That's how come this particular card can function as a full-blown computer. It already has a computer on it, a microprocessor, but we can create a brand new microprocessor with it. Now, this is a smaller one. You probably wouldn't be able to see, everything that you want to see on that. Let me show you the manufacturer of this, for example, a company called Jurassic. And as you can see here, they actually have quite a few different things. Some of them are very expensive. The ones that have enough capability, a large enough array, like this first one here, this DE10 Pro, that thing cost over $10,000. And it could also go right into a computer system. So it itself does not have its own microprocessor on it. It expects that you plug it into an engineering workstation. And then the operating system for the engineering workstation, this comes with a lot of advanced software that can talk right to it. But that's not the business I'm in. I was just trying to learn it. That's why I bought the educational model, which is considerably further down on this list. And it's right here, the DE10 Standard. And the DE10 Standard, we're talking now a more reasonable price. For the average Joe, which was me at the time, you pay about $350 for it. If you happen to be an active student, which I wasn't, I could have saved some money. In fact, I think the differential was even larger than that 3 years ago. That's the FPGA hardware. Here's an example of my board. This is a block diagram of it, of the DE10 Standard, all the things that it includes. I mentioned the CAD software. Well, the most popular one right now is called Quartus Prime, and it's available in 3 versions. It was originally made by a company called Altera, which later got acquired and is now Intel. Matter of fact, I think they've been removing the word Altera from most of their documentation. 3 years ago, it was on more than I saw this time when I went and looked at it to catch the latest versions of everything. But you can actually get Quartus Prime for free, the light edition, and it is not meant to actually fabricate chips. It doesn't produce what's needed to efficiently fabricate chips. I would not use that to try to make one. It would make one, but it would not be efficient at all. It would not be optimized because most of the optimizations are not included in this light edition. If you want to load this software down, it's very large. It's about 1.3 to 1.5 gigabytes. The latest version I got just today was version 19.1. You have to create an individual login account, though, with the Intel website when you go here before it'll let you load it down. But that's good because that'll also help you get the training. This shows you the training, and most of this I did 3 years ago. I went through all these modules of training that are available for free from Intel. At the time, this used to say Altera. Now it says Intel only. That's what I meant from what I said before. But there's some really good courses here, online courses. They're all free. They do have some they'll charge you for, which has a real live instructor-led courses. But I found these perfectly doable. They taught me everything that I needed to know. I do want to talk about this, and this is where there's been a lot of debate online lately. This is the reason that I made this video. I want to help people understand what Verilog is, or what VHDL as a whole is. But Verilog was the one that was in the news. I'll leave it up to you to figure out, if you're interested, to figure out what I'm referring to. But Verilog, along with VHDL, they are very difficult to work with. They require extensive professional knowledge if you're producing something professionally with them, like developing either a microprocessor, CPU, a graphics processing unit, Southbridge controller. That would be another one that's done with using Verilog. And it takes a significant amount of code and, more importantly, a lot of debugging to go along with that. The debugging is significant. You need an abundance of time, and you need some automated tools, and you need a lot of money, testing simulators, special hardware, whatever, in order to do this right. It's not something that's trivial. It takes a lot of time and a lot of effort. And as I said, the average CPU and GPU might be, a million or more lines of Verilog code. Now, this is where the rub is on this, because history has shown that despite all best efforts, they produce a chip, they've gone ahead and fabricated millions of them, and then later on they find out they have a flaw in their logic. It's happened to them all, believe me. They usually can counter a lot of those flaws because they cause functionality flaws, and they put in extra changes to the PC's firmwares, the BIOS, or to some of the software, the operating systems, in order to account for the flaw. And some of them they will never find, because unless the operating system or the applications try to use a feature in a specific crazy way, it may not realize that the processor doesn't work that way, that it causes something different to happen or leads to a fault that may or may not be handled by the BIOS or the operating system. Well, the way it works with all of this is there's going to be a certain amount of these flaws, probably only about 1%. But when you're talking about the average CPU chip could have a couple of hundred flaws to it, 2 or 3 of those can actually be what we call security vulnerability flaws. So just keep that in mind, that the Verilog code, it's not just what we call intellectual property, which means it's very important to the business and has a lot of investment on developing it, but you don't want that to get into the wrong hands. And then I'll leave it at that. Conclusions. Verilog is not used to create computer executable code. Verilog programmers must always think in terms of the actual hardware logic the descriptor language will produce. Computer and other digital logic hardware engineers, which most of them are, some of them are software, but most of them are hardware, they use Verilog to get their work done efficiently. The testing of Verilog is extremely limited. Keep in mind, I could download something to this card and I may not test a particular combination of logic. So if I really want to make sure it's something I want to sell to people, then I would make sure that I test every possible scenario of what I'm trying to do. I would never make a microprocessor, but I might make something that's a little handy little device of some sort. And I have several of those in mind. And then finally, errors in Verilog code are sometimes not realized until millions of large-scale integrated circuits have actually been produced. That has happened multiple times to the manufacturers of the CPUs, GPUs, and other equipment that we all use every day. Now, there are some references I'd like to pass along to you. If you're interested in learning more, well, you could start out. I'll start from the bottom. Programming FPGAs, this book right here. Very, very thin, very easy read. It's geared around a couple of special development boards. Not this one, but simpler ones that are available, and a little bit cheaper ones that are available out there. They give you examples of code for all 3 of them, and they show you exactly. They come with their own CAD software too. They don't use Quartus because they're not sophisticated to that level that they need that. So this will give you a good head start. You could just buy it and read it and play with it. If you're really, really into it, or if this is something you're interested in maybe someday doing as a career, for some of you high school and first or second year college students out there becoming a computer engineer, then these are the types of books you want to get into. Much more extensive, but this goes into, it gives you examples of code of how to make an entire processor, and they show you all of the HDL code. They show it to you in Verilog, and they show it to you in VHDL. So it gives you a really good example of looking them side by side as well. If this is something you ever consider that you want to do, or if you just want to take the PE exam, this was my best resource to learning those topics, was this one. Now, if you want to go to the next level of detail, then there's another book, Computer Engineering and Hardware Digital Design. It's also referred to, as the Patterson-Henderson book. And you'll see it referenced even in this book. You'll see this book referenced because that's how detailed this goes. So I have all three references up here on the screen. I'll also put them in the notes to this video, and we'll see if anybody's interested. If you are interested in learning more about Verilog or other VHDLs, I'm not a big person in terms of having practiced a lot with the VHDL version of the Hardware Descriptor Language, but I could, hold my own if I had to. Then just put a note down below in the comments to this video, and I'll be glad to go ahead and give you more detail on any of this. That concludes this video on what is Verilog and what is HDL as a whole, and how all this fits together, and a little bit on security related to that. If you got anything out of this video that you find useful or helpful in any way, it would be very helpful if you subscribe to my channel. My head will pop up here in a little bit. Click on it, follow along. It would really be helpful, and I'd be able to grow my channel appropriately and be able to produce better quality videos going forward. Well, thanks for watching, and until the next time, take care.